Alright, welcome back. Today we will be discussing or starting chapter 10, which involves the area of parallelograms, polygons, circles, all sorts of fun stuff. So 10.1 we're going to be doing area of parallelograms and triangles. I'm going to start off with triangles, and then part 2 will be on parallelograms. So let's get right to it. If we're starting off with triangles, most of you know, you've been learning pretty much, since 4th grade, that the area of a triangle, which I'll annotate like this, the area of a triangle is 1/2 base times height, right? It's 1/2 base times height. But, since we're in a geometry class, I think it would be fun to show why, because a lot of times you aren't shown why, you just kind of memorize this formula and you don't really know where it came from. So I'm going to give you an example with a right triangle and then show you a non-right triangle after that. So start off with a rectangle, which we know it's a rectangle. Well, I know it's a rectangle because it has a rectangle button on my app here, but you know it's a rectangle when I make these marks here. And that should be enough to know that. But let's look at what happens if we slice this rectangle along the diagonal. Let's see what happens here. Well, let me first do this. Let's call this side length H and this side length B. So we know that the area of this rectangle is what? In fact, I'm going to move this so it's not in the way. But we know the area of this rectangle is base times height, right? So we've known that before. Now, I'm going to call this triangle here triangle 1, and this triangle here I'm going to call triangle 2. Okay, so I have triangle 1 and I have triangle 2. Now, if I wanted to know the area of the rectangle in a different way, I could say that the area of the rectangle is the area of triangle 1 plus the area of triangle 2, right? It's just the two pieces added together. It's just, this half filled in plus this half filled in will give you the entire rectangle filled in, right? So that should be pretty self-explanatory. But if I want to know this, then what can I say about triangle 1 and triangle 2? Well, we already know that triangle 1 and triangle 2 have congruent sides, right? We know this side and this side are congruent. We also know that this side and this side are congruent because it's a rectangle. And we also know that they have congruent angles here and here. And since those angles are in between the two sides, we can say that triangle 1 is congruent to triangle 2 by SAS, right? Side angle side tells us that these two triangles are the same, which means that their areas are the same. So I can then say that the area of triangle 1 equals the area of triangle 2 since they're congruent, right? So if they're exactly the same, then their areas must be the same. So where does that lead us? That can lead us right back up to here, where it says the area of the rectangle is the area of triangle 1 plus the area of triangle 2. But if those are the same, I can substitute this and say the area of triangle 1 plus the area of triangle 1. All I did was substitute triangle 2 with triangle 1 because they are equal, right? So because they're equal, I can substitute that. And that tells me that the area of the rectangle is twice the area of triangle 1. Right? Area of triangle 1 plus the area of triangle 1 would just give me 2 times the area of triangle 1. So if I'm solving for the area of triangle 1, I could just divide both sides by 2 and get 1/2 the area of the rectangle is the area of triangle 1. But what is the area of the rectangle again? As we saw down here, the area of the rectangle is base times height, so I can just substitute that in and say the area of the triangle is just 1/2 base times height, which gives you the formula that you've known pretty much forever. Okay? I could have substituted for triangle 2 and gotten the same thing. So that kind of shows, I mean, another way of thinking about it is if I cut along the diagonal, then clearly this triangle is half of the rectangle, right? Clearly this triangle is half the rectangle, and if the rectangle has an area of base times height, then the triangle must have half of that area, which we just proved on the right side here. So that's easy to show on a right triangle. What if it's not a right triangle? So all triangles, that's the question. Does this work for all triangles? Well, if I have, let's say, this triangle here, right? And I'm not going to go into such a detailed proof, I'm just kind of explain how to figure this out. If I wanted to know the height of this triangle, right, then what I would need to do is, again, we should remember this from our study of altitudes, that the height just means you have to meet at a right angle, right? So this here would be the height, right? But if I'm drawing a rectangle, which I'll do in a different color here to make it clear. If I'm drawing a rectangle, oh man, it didn't work. I'll do it with pen. Around this triangle, then really what we can do is we can see that this rectangle is clearly divided into two parts, right? I have this part over here, and I have this part over here. So I clearly have two different parts, not necessarily halves, but two parts, right? And with those two parts, if I look in there, I can treat this part on the left as a separate side, right? Where really this is a rectangle here. This is a rectangle, and it's cut with a diagonal, which we just showed that this triangle in here would be half of the entire triangle, right? So this, if I'm going to do this side in pink, that this triangle that I just colored in green here is half of that pink rectangle, right? Well, the same thing goes here. This, if I'm looking at the other half, let's do it in blue here. If I'm dealing with this rectangle in blue, then this triangle that I'm going to fill in blue is, you can flip back to the other side, is clearly half of that blue rectangle. So this giant rectangle that I will go in white here, this giant rectangle here has two parts, each cut directly in half, which means the area of this original triangle is half of that rectangle. Well, what are the dimensions of that rectangle? Well, if we have this whole side length as our base, and this is our height, well, this is also the height that I've scribbled over multiple times inside, so it's still 1/2 base times height. Right? So it works for all triangles. All that to say, it works for all triangles. So that's kind of a little geometry twist to it as to why this works. Quick thing here, when you're looking for height, because a lot of times it's not going to be drawn for you, you're going to have to figure it out yourself. On a right triangle, it's not so bad. If we have a right triangle, again, remember that height always means 90 degrees. 90 degrees. Do not forget this. Height always means 90 degrees. Okay? So if I have a right triangle here, then I already have two things that I consider the height. I can consider this one the height because it meets at 90 degrees here. Or, if you want to think more sideways, if you will, this one can also be considered the height, and this one would be our base. So these two in this case would be interchangeable because they meet at 90 degrees. So your two legs in a right triangle will be considered your base and your height. Okay. So what if we're dealing with an acute triangle or an obtuse triangle? Well, that's where it can get a little more tricky. Actually, I forgot something about the right triangle. If I have a right triangle here, those aren't your only two options for the height. So again, this is a right triangle. I could have drawn the height from this point, this at the 90 degree angle. I could have drawn it here to meet at 90 degrees. If I draw the altitude from, let's call this point X, right? If I draw the altitude from there, this could also be deemed as our height. And if that were the case, then this side here would be our base. Okay, so there's three options on every triangle. Let's look at other cases here. Oh, I don't want to go to the next example yet. Let's look at some other cases. So what if I have an obtuse triangle, right? Well, the first case would be something like this. an obtuse triangle, usually it's most common for students to just say, okay, just slice it right there because, you know, that's the top, if you will. We have a right angle here. So this would be the height, and this whole side down here would be the base, right? So that's one example of what you could do there. The other example, if I wanted to start at, you know, at like this point here, right? If I want to draw the height though, no lines in here are going to meet at 90 degrees, right? They all form obtuse angles there, so none of those are going to work, which means we need to do something called extending our original line. So if I extend this original line further, right? If I extend this further, then I can draw it down here to meet at 90 degrees, meaning this length here would be our height. Okay, so if it doesn't work inside the triangle, then you have to extend one of the legs, which gives you it. But this side length here would still be our base. It would not include this blue highlighted part. That's not included in our base. So this side length here would still be our base. That's the one that we extended, right? We extended it out here to get to our height, which is kind of a trickier part. Okay, so it's just a different way of looking at it. Now let's go from the other length here, or the other vertex here. So if we go here, again the same thing is going to happen, right? So if we extend in here, none of these are going to be 90 degrees, so we can't use those, which means we are going to need to extend this side length, drop the height down here, perfectly drawn, of course. This is our height. This would be our base here, right? Not the added section on the outside. So it's usually easiest to just deal with the height coming straight down inside the triangle, which in this case is here. That's usually the easiest case because you don't have to extend any side length. But that's not necessarily always an option. What if you're dealing with an acute triangle? So let's say we have something like this. Acute triangle is not so bad because all three, let's say I'm going from this point first, the height here would be dropping at 90 degrees, right? Drawing the altitude would be there. Well, what if I'm going from this side? Oh, in this case, this would be the height. You know, going with the original we did. This would be the height. This would be the base because these meet at 90 degrees. Right? Well, what if I had from here, drop it at 90 degrees. This would be the height. This would be the base. So my height and base are constantly changing. What's cool about this is that my area is not changing. So if I go from here, I can drop it right there, 90 degrees. This is my height. This is my base. Again, because that's where they meet at 90 degrees. Okay, so it's just kind of a brief overview. Let's do a problem, because that's fun. So example 1. We have a triangle given 60 degrees there, 12 down below, and 4 at 3 for a side length. So when we're looking at this triangle, we want to find the area, right? So again, first we need to draw the height somewhere. We need to draw the height. I think it's easiest to draw the height here. Again, because we know it's going to be inside the triangle. It drops straight down, and this is an easy base to work with because it's a nice number. Okay, so that is our height. Let's call it h, right? Which means 12 is our base. So let's call that b. So all we need to do is find h, and then we have the formula a equals 1/2 bh. As soon as we find h, we can plug it into the formula. Okay, so we're going to use a little bit of our special right triangles here. We have a 30, 60, 90 triangle, right? We know this is 90. We know this is 30. Excuse me, 30. So this side length here is the hypotenuse. To get from the hypotenuse to the short leg, this should be review. You just need to cut it in half. So this side would be 2 rad 3. And then to get from the short leg to the long leg, you multiply by rad 3. So you'd say h equals 2 rad 3 times rad 3, which is 2 times 3, which is 6. So the area here would be 1/2. The base is 12. The height is 6. You get 1/2 of 6. Oh, man. I can't multiply. I can do geometry, can't multiply. You get 6 times 6, which is 36 units squared. So look at part 2. We'll give you another example, and we'll start talking about parallelograms. All right? Have a good one.